Hello, dear friends. See lecture number 1, chapter number 6. Application of differentiation, derivative. Clear? Before starting one topic, I would like to define first of all increasing function. All of you are familiar with this thing, even though let us recall it. Let us consider f is function from R to R. Consider f of x is equal to x square. Now see here, this x comes from this R and that is known as domain, and this one goes in codomain, and x is called pre-image and f of x is called image. Now see, what is f of 1? 1, f of 2, 4, f of 3, 9, f of 4, 16, likewise. Now see here, see this pre-images increases 1, 2, 2, 2, 2, 3, 3, 2, 4. At that time images also increases. Whenever pre-images increases, at that time images also increases, then that function is called increasing function. But that thing in word form. How to write it in notation form? See, pre-image increases, that is 1 less than 3 less than 4 and so on. Pre-images increases, at that time images also increases. That means this implies f of 1 less than f of 2 less than f of 3 less than f of 4 and so on. That means see here, order sign less than that remains same. That means whenever order sign remains same, at that time that function is known as increasing function. Let us define. If for function f from R to R for all x1, x2 belongs to R, x1 less than or equal to x2 implies fx1 less than or equal to fx2, then that function is known as increasing function. Then f is said to be an increasing function. All of you are familiar with this definition. But see, here observe less or, here also less or equal to, here also less or equal to. In that case it is increasing. See here, if we draw the graph of this function, see, up to this part image remains same, then increases, that increases, then increases, that is increasing function. Now our aim is to second thing define strictly increasing function. Strictly increasing function. Now see here, on same line, only strictly less we have to use inequality. If for function f from R to R for all x1, x2 belongs to R, x1 less than x2 implies fx1 less than fx2. Then f is said to be strictly increasing function. Now you can see here only strictly x1 less than x2, at that time fx1 less than fx2. That is the strictly increasing function. Order sign remains same. Here less than, so here also less than. Here less than or equal to, here also less than or equal to. In that case it is increasing function, in that case it is decreasing, strictly increasing function. Now let us come on differentiation. Before that thing, this one is for set of real number, but what can you say about for interval? If for all x1, x2 belongs to open interval AB, any open interval, x1 less than or equal to x2 implies fx1 less than or equal to fx2. Then f is said to be an increasing function on open interval AB. Clear? This one is for real valued function from R to R. Here for open interval. Same thing, next note. If for all x1, x2 belongs to open interval AB, x1 less than x2 implies fx1 less than fx2, then f is said to be strictly increasing function on open interval AB. On open interval AB. Clear? Next thing, what is the application in terms of differentiation? If f dash x greater than or equal to 0 for all x belongs to R, or for all x belongs to open interval AB. First derivative is positive, then it is said to be an increasing function on R or on open interval AB. જો અહીંયા interval for all x belongs to R લેવામાં આવે, then it is increasing on R. If you take all x belongs to R, then it is increasing on R. If you take open interval, then it is increasing on open interval. Greater or equal to 0, non-negative. But see one thing, here we are not going to prove this inequality. Why first derivative is greater than or equal to 0, then it is increasing or decreasing. Let us accept it, because that depends on mean value theorem, and as far as our syllabus is concerned, mean value theorems are omitted. So directly keep this thing in mind. If first derivative greater than or equal to 0, then it is increasing. Second thing, if f dash x greater than 0 for all x belongs to open interval AB, or for all x belongs to R, then f is said to be strictly increasing function on open interval AB. Clear? Same way, let us define decreasing function. If for f from R to R, see here, if the order sign remains same, then it is increasing. If order sign differ, here less than or equal to, and here we get greater than or equal to, then it is decreasing function. Now see, before that thing, let us consider one example. F of x is equal to 1 by x, f of 1, 1, f of 2, 1 by 2, f of 3, 1 by 3, f of 4, 1 by 4. Now see, whenever pre-images increases, at that time images decreases. That means 1 less than 2 less than 3 less than 4, that is increasing order, implies f of 1 greater than f of 2 greater than f of 3 greater than f of 4 greater than, and so on. Then it is called decreasing function. See here order sign changes, here less, here greater than or equal to. So let us define it. If from R to R, for all x1, x2 belongs to R, x1 less than or equal to x2 implies fx1 greater than or equal to fx2. Then f is said to be decreasing function. Clear? On same line, if for f from R to R, for all x1, x2 belongs to R, x1 less than x2 implies fx1 greater than fx2. Then f is said to be strictly decreasing function. Clear? Yes. Now that is on R. Now not so if for all x1, x2 belongs to open interval AB, x1 less than or equal to x2 implies fx1 greater than or equal to fx2, then f is decreasing on open interval AB. Clear? Second thing, if for all x1, x2 belongs to open interval AB, x1 less than x2 imply fx1 greater than fx2, then f is strictly decreasing on open interval AB. That means on open interval AB, if this thing happens, then it is known as decreasing function or strictly decreasing function. Now likewise one note, see here, first derivative greater than or equal to 0, then it is increasing, and first derivative only strictly greater than 0, then it is strictly increasing. Now come on here, next note, if f dash x greater than or equal to 0, less than or equal to 0 for all x belongs to open interval AB, then f is decreasing on open interval AB. And if f dash h is strictly less than 0 for all x belongs to open interval AB, then f is strictly decreasing on open interval. Now, one more note that we know if f dash x equal to 0 for all x belongs to open interval AB, then f is constant on open interval AB, because we know that the derivative of constant term is 0. Now, dear friends, keep thing in mind. To show strictly increasing function, prove that first derivative is greater than 0 or check whether it is greater than 0 or not. If you get greater than or equal to 0, then it is increasing. Now see here, whenever derivative is less than or equal to 0, strictly less than 0, then it is either decreasing or strictly decreasing. And derivative equal to 0, then it is constant term. Clear? Yes. Now see here, let us start exercise textbook NCERT exercise 6.2. Exercise 6.2 based on increasingness, decreasingness. Now see here, illustration number 7 to 30. Illustration 7 to 13 for you, for homework. Today we are going to see some examples, then you are able to solve these illustrations also. First sum, very simple sums are there. So that the function given by f of x is equal to 3x plus 70 is strictly increasing on R, strictly increasing on R. That we want to see. Recall that note, if first derivative is greater than 0, then it is strictly increasing. First derivative is less than 0, then it is strictly decreasing. Here, f of x is equal to 3x plus 70. This implies f dash x is equal to 3 and it is greater than 0. And therefore f dash x is greater than 0 for all x belongs to R. Very simple. And therefore f is strictly increasing on R. Similarly, second sum, prove that f of x is equal to e raised to 2x is strictly increasing on R. Here f of x is equal to e raised to 2x. Implies f dash x is equal to e raised to 2x. derivative of e raised to some function is e raised to some function d by dx of some function, that is 2 e raised to 2x. Now for all x belongs to R, e raised to 2x is greater than or greater than 0. This implies 2 e raised to 2x. 2 e raised to 2x is greater than 0. And therefore, f dash x is greater than 0 for all x belongs to R. And therefore, f is strictly increasing on R. Clear? Next sum. Here we wish to see that, prove that f of x is equal to sin x is first part, a part, strictly increasing in open interval 0 to pi by 2. B part, strictly decreasing in open interval pi by 2 to pi. See, you already noted in a, that means you already seen this thing in 11th science. In first quadrant, sine function is increasing, in second quadrant it is decreasing. Now see here, f of x is equal to sin x. This implies f dash x is equal to cos x. We know that for all x belongs to 0 to pi by 2, or cos x. Now cos x is greater than 0 for all x belongs to 0 to pi by 2. First quadrant cos function positive, and therefore f dash x is greater than 0 for all x belongs to open interval 0 to pi by 2, and therefore f is strictly increasing in open interval 0 to pi by 2. Second thing, in second quadrant we know that cos function is negative, pi by 2 to pi. This implies f dash x is less than 0 for x belongs to pi by 2 to pi, and therefore f is strictly decreasing in pi by 2 to pi. Clear? That means same way they can ask for any trigonometric form. This is the way to check whether it is strictly increasing or decreasing in a particular interval. Only we need to check that whether derivative is positive or negative, nothing else. So these are the very, very simple things are there. Of course, C part is also there for this example. Sorry, C part is also there. C part says that neither increasing nor decreasing in open interval 0 to pi. So let us see here. Also, if x belongs to 0 to pi, for all x belongs to 0 to pi, f dash x is not greater than 0 and f dash x is not less than 0 for all x belongs to in this interval. આ interval ના થોડાક પાર્ટ માટે greater than 0 છે, થોડાક પાર્ટ માટે less than 0 છે, and somewhere it is 0 also. So for all x belongs to open interval 0 to pi, for all x belongs to 0 to pi, we cannot conclude that f dash is greater than 0 or less than 0, neither greater than 0 nor less than 0. And therefore f is neither increasing nor decreasing in 0 to pi. Clear? Now next example, find the intervals in which the function f given by f of x is equal to 2x square minus 3x is a part strictly increasing and b part strictly decreasing. That means, now see here, observe previous sum. Here they are asking that prove that it is increasing function, strictly increasing function on R. Clear? Here they are asking that prove that it is strictly increasing in given open interval or decreasing in given open interval, or neither increase nor decrease in a given open interval. In this example, we want to find a intervals where this function increase or decrease, and this is the important topic. And definitely one example of 4 marks, maybe they are going to ask from this section. Clear? So let us see. Very simple thing. First of all, find out derivative of a given function. What is f dash x? 4x minus 3. Now draw a real line. So that is minus infinity to plus infinity. Now check where this function is 0, that 0 at 3 by 4. Clear? Put on this interval. That means at x is equal to 3 by 4, this function is derivative is 0. So we cannot talk at 3 by 4 it is greater than 0 or less than 0. Definitely it comes out equal to 0. Now here two interval forms, minus infinity to open interval 3 by 4, this open interval, and 3 by 4 to infinity, that is the second part. Clear? Now let us see first one. For all x belongs to minus infinity to 3 by 4, this says that x is less than 3 by 4. This says that 4x less than 3. This says that 4x minus 3 less than 0. And that is our derivative. Say result number 1. And therefore by 1, f dash x is less than 0. And therefore f dash x is less than 0 for all x belongs to where? Minus infinity to 3 by 4. So in this interval it is strictly decreasing, and therefore f is strictly decreasing in interval minus infinity to 3 by 4. We want to find intervals where it is strictly increase or decrease. Now, what is second part? For all x belongs to open interval 3 by 4 to onwards, that means up to infinity. This says that x is greater than 3 by 4. This says that 4x greater than 3. This says that 4x minus 3 greater than 0. And therefore by 1. F dash x is greater than 0 for all x belongs to where? To where? 3 by 4 to infinity. In this interval it is positive, and therefore f is strictly increasing in which interval? 3 by 4 to infinity. This one is very simple example. Let us see next example. Find intervals in which following functions are strictly increasing or strictly decreasing. First one, f of x is equal to 2x cube minus 3x square minus 36x plus 7. Second one, f of x is equal to x square plus 2x minus 5. Third one, f of x is equal to 10 minus 2x minus 2x square, 10 minus 6x, 10 minus 6x minus 2x square. Fourth one, fx बराबर 6 minus 9x minus x square. Fifth one, f of x is equal to minus 2x cube minus 9x square minus 12x plus 1. Sixth one, f of x is equal to x plus 1 whole cube, x plus x minus 3 whole cube. Clear? On same line, f of x is equal to seventh one, 4x cube minus 6x square minus 72x plus 30. Definitely 100% one example based on this pattern. Find intervals where it is increasing or decreasing. Now see here. Next, before starting, let us start one example. Let us see first one. F of x is equal to 2x cube minus 3x square minus 36x plus 7. Now see here. What is derivative? F dash x is equal to 6x square minus 9x minus 36. Here not 9x but 6x. 6x square minus 6x minus 36. 6 common. X square minus x minus 6. Now main thing, factorize it. We have to check where it is 0. X minus 3, x plus 2. Say the result number 1. Clear? Now see here. Now draw the real line. Plus infinity to minus infinity, where it is 0, at minus 2, at 3. So in our case, how many parts are there? Minus infinity to minus 2, minus 2 to 3, and 3 to infinity. 3 parts are there. Let us take one by one. First one, for all x belongs to minus infinity to minus 2, x is less than minus 2. X is less than minus 2. Definitely it is also less than 3, as minus 2 less than 3. So what we have? We have a x less than minus 2, x less than minus 2, and x less than 3. So this implies x plus 2 less than 0, x minus 3 less than 0. This implies x plus 2 into x minus 3 positive. Product of two negative quantities positive. And therefore by 1, f dash x is greater than 0 for all x belongs to where? Minus infinity to minus 2. And therefore f is strictly increasing in which interval? Minus infinity to minus 2. Second case, what we have to take? Minus 2 to 3. Second case, for all x belongs to minus 2 to 3, open interval. This says that minus 2 less than x less than 3. This says that x plus 2 greater than 0, x minus 3 less than 0. The product of one positive quantity and one of the negative quantity is negative. And therefore by 1, f dash x is less than 0 for all x belongs to where? Minus 2 to 3. Open interval minus 2 to 3. And therefore f is strictly decreasing in open interval minus 2 to 3. Third part, where we have to take it? Third part, 3 to infinity. For all x belongs to open interval 3 to infinity. This says x greater than 3, that is greater than minus 2 also. So x minus 3 greater than 0 as well as x plus 2 is also greater than 0. And we know that product of two positive quantity is positive. And therefore by 1, f dash x is greater than 0. F dash x is greater than 0. Kona mate? For all x belongs to 3 to infinity. And therefore f is strictly increasing in 3 to infinity. Now see here, find intervals where this function is increasing or decreasing. Already solved first one. Clear? Now here you get the derivative 2x plus 2, very easy, like as very first sum. Here derivative comes out minus 6 minus 4x, so once again very easy. Check where it is 0. Here also two parts are there on real line, minus infinity to infinity, here 1. Here it comes out f dash x is equal to 0. If we take it, minus 6 minus 4x is equal to 0. 4x is equal to minus 6, x is equal to minus 3 by 2. So somewhere minus infinity to infinity, somewhere minus 3 by 2. So check it, very easy for you. So I am leaving that part for you. Now fifth one is same as to first one, we already solved. Clear? Now seventh one is also on same line. So I would like to leave fifth one for you, seventh one for you. Let us see example number 6. Example number 6. F of x is equal to, what is given? F of x is equal to x plus 1 whole cube into x minus 3 whole cube into x minus 3 whole cube. Now see here, find out directly derivative, apply product rule, derivative of first term, second term as it is. Now first term as it is, derivative of second one. Agree? Yes. Now something is common. 3 into x plus 1 whole square, x minus 3 whole square common. What you get here? Here we get x minus 3 and from here we get x plus 1. So that is equal to 3 into x plus 1 whole square, x minus 3 whole square to x minus 2. And that is equal to, take 2 common, x plus 1 whole square, x minus 3 whole square, x minus 1. So now check it. Draw a real line where it is 0, at minus 1, at 1, at 3. So minus infinity to infinity. How many parts are here? So this example is important. Minus infinity to minus 1. Second one, minus 1 to 1. Third one, 1 to 3. Fourth one, 3 to infinity. So let us see one by one. First part. For all x belongs to where? Minus infinity to minus 1. This implies x less than minus 1. Minus 1 is less than 1 as well as 3. Less than 1 as well as 3. So this says that x plus 1 less than 0, x minus 1 less than 0, x minus 3 is also less than 0. Now see here, this says that x plus 1 whole square greater than 0, x minus 1 less than 0, x minus 3 square greater than 0. And therefore by 1, this implies x plus 1 whole square, x minus 3 whole square, x minus 1 is less than 0, because this one is positive, this one is positive, and this one is negative. So two of positive quantity, one of them is negative quantity, so their product is negative. And therefore by 1, f dash x is less than 0 for all x belongs to minus infinity to minus 1. And therefore f is strictly decreasing in minus infinity to minus 1. Second part, where to where? For all x belongs to minus 1 to 1. This says that minus 1 less than x less than 1 less than 3. So this says that x plus 1 greater than 0, x minus 1 less than 0, x minus 3 less than 0. And therefore, or this implies, we can write here x plus 1 whole square, x minus 3 whole square into x minus 1, which is less than 0. Because x minus 3 less than 0, so x minus 3 whole square greater than 0. X plus 1 whole square, that is product of two positive quantity with one of the negative quantity. That comes out less than 0. And therefore by 1, f dash x is less than 0 for all x belongs to minus 1 to 1. And therefore f is strictly decreasing in open interval minus 1 to 1. Third one is 1 to 3. Third one. For all x belongs to 1 to 3. This implies 1 less than x less than 3 and minus 1 less than 1. So x plus 1 greater than 0, x minus 1 greater than 0, x minus 3 less than 0. But this says that x plus 1 whole square, x minus 3 whole square, x minus 1 is positive. X minus 3 less than 0, but their square is positive. And so product of positive quantity is positive. And therefore by 1, f dash x is greater than 0 for all x belongs to open interval 1 to 3. And therefore f is strictly increasing in open interval 1 to 3. Now you can see here, last one is 3 to infinity. Let us see fourth part. For x, all x belongs to 3 to infinity. This says x greater than 3, greater than 1, greater than minus 1. This says that x minus 3 greater than 0, x minus 1 greater than 0, x plus 1 greater than 0. All these things are positive. And this implies x plus 1 whole square, x minus 3 whole square, x minus 1 less than 0. Sorry, greater than 0. And therefore by 1, f dash x is greater than 0 for all x belongs to 3 to infinity. And therefore f is strictly increasing in 3 to infinity. Very important example. Clear? Today let us leave up to this stage. Rest of what we are going to see next time.